Okay, so in this video, we're going to continue talking about free body diagrams, and we're going to do some more examples with free body diagrams before you work on your practice worksheet over free body diagrams that you should have got picked up in class last time. And then we're going to start talking about net force and Newton's second law. Okay, so before we get into that, I want you to take a look at this do now question that we have today. And this question says that the free body diagram shows all forces acting on a box supported by a stationary horizontal surface where the length of each the length of each force vector is proportional to its magnitude. Which statement below is correct? Okay, and so I want you to look at the answer choices. This question is actually taken from a past AP physics exam, and so it's not quite aligned with OnRamps physics, but it is pretty closely aligned conceptually. Okay, so I want you to look at this free body diagram and see if you can answer this question. Okay, so the correct answer to this question is C. The box must be moving to the right as indicated by the force of friction in the opposite direction. Now, the force of friction, as it talks about in the notes, always opposes motion or attempted motion. And so the fact that the force of friction shown here is going to the left indicates that the box must be moving or trying to move to the right, because friction always acts in the exact opposite direction of motion. Now, the other answer choices don't make sense. A says the box must be moving to the left. If you look at this FBD, what this free body diagram is showing is that this object is accelerating to the left. There is a net force on the box to the left. That is not the same thing as the object moving to the left, though. Remember, a free body diagram does not indicate which way an object is moving. It only indicates the forces acting on an object, and therefore it can also indicate which way the object is accelerating, but velocity and acceleration are not the same thing. Okay, and so I don't want you to look at this and be like, oh, there's an arrow to the left, it must be moving to the left, because that's not the case. B is wrong because the box cannot be accelerating to the right because the net force is to the left. There's not even any forces to the right at all. And then D says there can be no force of friction unless the box is moving. It can be inferred from context that because there is a force of friction, that the box is in fact moving. And you might have looked at the word stationary and thought the box was not moving, but it just says that the surface is not stationary. And notice we have a force of gravity because we always do, and we have a normal force because we have a surface. Okay, we always have a normal force when we have a surface perpendicular to the surface, and then friction always opposes motion. Okay, so pause it there if you need to look at that some more. Okay, so moving on. Okay, so we've been looking at free body diagrams, and you should have already taken notes from this slide as far as different types of forces are concerned. If you've not already done so, please add this to your notes at this time. Pause it here. Okay, so just a couple things I want to point out. Notice that you always have a normal force when you have a surface. Okay, and so that is the reaction force from a surface on anything pushing on it. The normal force, the word normal in mathematics means perpendicular, and so the normal force always acts perpendicular to the surface, meaning at a 90-degree angle to the surface. Tension is a force you have when you have a rope or a string. Friction, we'll talk a little bit more about later, but friction always opposes relative motion, and there's actually two types of friction. Static friction, which is a type of friction you have when an object is not moving. For example, if you try to push on a desk and it doesn't move, then it could be the force of static friction is preventing it from moving. When you have a moving object that has friction acting on it, that's what's called kinetic friction. Okay, so static means not moving, kinetic means moving, and so the name is kind of self-explanatory. Okay, as are the other forces shown on this slide. Okay, so we've already done a few free body diagram examples, but let's take a look at a few more. Okay, so we've already taken a look at example 1, and example 2 we can do really quickly. It says a skydiver is falling with a constant velocity. When I'm looking at a problem and I see words like, remains at rest or constant velocity, my mind immediately goes to Newton's first law, which says, among other things, that an object in motion will remain in motion at a constant velocity unless acted upon by a net force. Meaning that the skydiver, if it's falling, we can infer just based off of this word constant velocity that the net force on the skydiver is zero, because Newton's first law says that has to be the case. That means my free body diagram, I would normally include gravity just because. But there has to be another force acting on the skydiver, allowing it to fall with a net force of zero. Okay, now your first guess might be normal force, but remember, you only have a normal force when there is a surface involved, and there's no surface here because the skydiver is in the air. There's no rope, so there's no, tension force, and the problem actually says consider air resistance, okay, which is not one of the forces we talked about, and so if it's not one of the forces on that list, you can just kind of go along with it. Notice that my arrow is more or less the same length. I say more or less because I'm not good at drawing. And I'm going to label that F air. I could also call it F air resistance, or sometimes it's called drag. Um, but in any case, that's basically what the free body diagram would look like for this situation. Notice, by the way, that there's not really a way to indicate how fast the skydiver is falling based off of the free body diagram. All I know is that the skydiver is falling with a constant velocity. Okay, so pause there if you need to look at that some more. Okay, example 3 we've already done in class, so you should already have that in your notes. Okay, this is example 3.5. It says a man using a rope. Immediately I'm thinking there's going to be tension. Drags a sled to the left across a rough surface. Okay, so these are all context clues we're looking for. Rough surface implies friction, causing it to speed up. And we're asked to draw a free body diagram for the sled. Now the sled is on the ground, obviously. Okay, and so we have force of gravity going down. Because it's on the ground, there's a surface, and so there's going to be a normal force perpendicular to that surface. So I have normal force going up. And then the man is dragging the sled with a rope to the left, meaning there's going to be a force of tension to the left. We also know there's friction because it says there's a rough surface. Now, the only way to really mess this up is to mess up the length of the arrow. Because the sled is going to speed up, that means it is accelerating. And we know from Newton's first law that if the object is accelerating, the only way it can change its velocity is if the net force on the object is not equal to zero. Right? That comes straight from Newton's first law. That means when I draw this, I actually need to draw it so that there's a net force to the left, because if it's moving to the left and the net force is to the left, that means it's going to speed up, which is what it's supposed to do. And so I need to make sure to draw this with a net force to the left. And so that means I need to draw the force of friction. That arrow needs to be shorter than the force of tension. And actually, I'm going to label that FFK for kinetic friction, force of kinetic friction. I know it's kinetic friction because it's moving in this situation. And so that's what the free body diagram would look like in this situation. Pause it there if you need to look at that some more. Okay, so here is example 4. And normally I would try to have you do this on your own. I would ask that you pause it at this point and try to do this example 4 on your own in your notes. And then I will go over example 4 in just a minute. Okay, so we were asked to draw the free body diagram for a man standing in an elevator, which is moving upwards, but slowing down. Okay, so let's start with, just kind of listing the forces we know have to be acting on the man. Force of gravity, and let's see, the man is standing on the bottom of the elevator, which means he's standing on a surface, which means there's a normal force on the man. And if you think what other forces might be acting, you might think, there's tension, right? Because, the top of the elevator is held up by a cable, and so there should be tension because of that. But notice that we're asked about the free body diagram on the man. And even though there is an elevator cable holding the elevator up, there's not that force is not acting on the man, it's acting on the elevator. And so if we were to draw the free body diagram for the elevator, we might include tension, but we're not going to in this situation. And so these are the only two forces we're concerned with. Okay, so I'm going to have force of gravity going down just to start with. And then let's see if we can interpret this correctly. The elevator is moving up, but slowing down. Which way it's moving does not necessarily indicate one way or the other how I should draw my free body diagram. However, if it's moving up, but slowing down, we talked about this last class, but if an object is slowing down, that means its velocity and its acceleration are in opposite directions, right? And so if your velocity and acceleration are in the same direction, you're going to speed up. And if your velocity and acceleration are in opposite directions, you're going to slow down. And so based off of the fact that the man is going up, but he's slowing down, that kind of indicates to me that his velocity is up, but his acceleration is down. Now, what that means is I need to make sure to draw this free body diagram such that he is accelerating down. And so what that means is if the force of gravity is going down and the normal force is going up from the surface, I need to make sure that this arrow is shorter than the force of gravity. And so this is what example 4 should look like. Okay, notice the arrow for the normal force is shorter than the arrow for the force of gravity. Now you might look at that and be like, wait, I don't understand. How is he moving up if the force up is less than the force down? Well, remember, again, the free body diagram does not have anything to do with which way the object is moving, only the force is acting on the object and which way the object is accelerating. He might be moving up, but his acceleration is down. Okay, so you cannot discern from a free body diagram anything about velocity or which way the object is moving, only which way he is accelerating. And based off the context of the problem, I know he has to be accelerating down because he's moving up but slowing down. And so this is what the FBD should look like for example 4. So pause it there if you need to look at that some more. Okay, and then finally, we're going to take a look at example 5. I want you to try to answer example 5 on your own, and then I will discuss the answer momentarily. Okay, so the answer to this question is actually 5. And the reason for that is that if you look in your notes about what it talks about with forces, first of all, force of gravity always goes down. And even though there's not like labels on any of these FBDs, you can still kind of infer from context that the arrow down is the force of gravity. The surface, which there is a surface, is at an angle, and this is actually what we'll call an inclined plane later on. And remember that the normal force, which you always have normal force when there's a surface involved, the normal force is always perpendicular to that surface. It's always at a 90-degree angle to the surface. And so if the surface is at an angle, that means the normal force should also be drawn at a 90-degree angle to that surface. And so it's going to be tilted. And so this arrow right here could indicate the normal force. This arrow could indicate the force of gravity. And if he's going down the incline, then if there's friction acting on him, that would oppose his motion, and so that would be in this direction, like so. Okay, so pause it there, and let me know if you have any questions about example 5. Okay, so hopefully at this point you feel more comfortable with free body diagrams. Here are just some extra notes as far as free body diagrams go. You should be able to finish your free body diagram worksheet that you got in class last time. I'm going to give you some time to work on that and check your answers. However, I do want to move on to net force and Newton's second law in short order. So what I would do if I were you is I would stop this video, or finish this video, I should say, work in your free body diagram worksheet and check your answers to that worksheet, and then right after that, start the next video talking about net force and Newton's second law. Um, probably um, the most important part of this unit has to do with free body diagrams and Newton's second law, and so I would definitely make sure that you fully understand free body diagrams before you move on. But we do have quite a lot to get through in this unit, so please make sure that you move on to that next video as soon as you finish your free body diagram worksheet and check your answers. All right, so as always, please let me know if you have any questions, and I will see you guys in the next video.